Hello again, class. So everything we covered in 14.8 in terms of Lagrange multipliers is also applied to functions of three variables. The method is in the process is exactly the same, but the algebra is a little bit more intense. Okay, and the reasoning behind it is the same, except that now it uses level surfaces versus level curves. So to find an absolute max and min of a function of three variables subject to some constraint, which now this will be the equation of a level surface, and assuming that these extreme values do actually exist, and in order to use this Lagrange multiplier method, we don't want the gradient of g to be 0. If these things apply, then what we can do is we can find these points where you're going to have an absolute max and min by seeing where the gradients are scalar multiples of one another and satisfying the constraint equation. Okay? Once you find those points, again, you're going to evaluate them into your function f to determine which ones are giving you the absolute max, which ones are giving you the absolute min. So I want to show you just one example where, because it's pretty intense algebraically, and we can do some more in class depending on the time. So I want to look at this one. It says, find the absolute max and min of this function f given by x to the fourth plus y to the fourth plus z to the fourth, where these points have to satisfy this constraint equation, which if you look carefully is the equation of a sphere of radius 1. So all the points that I'm plugging into this function of three variables need to come from points that lie on my sphere of radius 1, okay? And we are trying to find which of the points that lie here will give me an absolute max and absolute min. So as we did before, here's my constraint equation. I'm going to let this side with all my variables be the constraint function. Okay, whoops, I wrote to the fourth here. This should say, these should be squared. Okay, so these should all be squared. Okay, good. And so now that we define g, we're going to find points x, y such that the gradients are equal to one another, are scalar multiples of one another. And so we need the partials with respect to x to be scalar multiples, partials with respect to y, and the partials with respect to z to all be scalar multiples in terms of lambda. And those points need to lie on my constraint equation. When we go ahead and we take the partials with respect to x, notice you're going to get 4x cubed. You're going to get 4y cubed for the partial with respect to y, and 4z cubed for the partial with respect to z. When you find the partials of g with respect to x, you get 2x times my lambda, that's this guy right here, 2y times my lambda, and 2z times my lambda for the other partials. And again, they're subject to my constraint equation. All I did from here to here is I just simplified a little bit by dividing everything by 2. And so we ended up with this cleaner system of equations. Okay. Notice that it would be very hard to isolate the x and the y and the z and then plug them in here and then try to figure out the actual value of lambda. It's going to be very challenging to take that path. But also it's pretty challenging to isolate lambda because I need to divide by x, y, and z if I do that, and I need to be very careful if I want to do that. So either path you take is going to be a little nasty. But I think the one that's a little more doable is the one where we try to at least isolate lambda. And so therefore we need to consider x, y, or z being 0. So let's start with the case where all three of them are 0. Is that even a possible solution point? So if all three of them are 0, notice that that wouldn't satisfy my constraint equation because I'll get 0 equals 1. And so 0, 0, 0 is not a solution. Okay? But also notice that lambda itself can't be 0, because if lambda is 0, that will be 0, 0, 0. And let's say, for example, this one right here. If lambda was 0, that would give me that 2x cubed has to equal 0, which would tell me x has to equal 0. And so if I do the same thing with this one and this one, I'll again have to conclude that x, y, and z are 0. But we just said that that can't happen because it wouldn't satisfy this constraint. So that's why lambda cannot be 0 as well. Okay? So we know this and we know this. Okay. But what's important is that we know that all three variables at the same time can't be 0. So we got to split it up into different cases because now we have three coordinates. So case 1, 2 of the variables are 0 and one of them is not 0. Okay? That can happen in different ways. Either x and y are both 0 and maybe z isn't, or x and z are 0 and y isn't, or y and z are 0 and x isn't. So there's this case itself has its own cases that can happen. Let's just pick one and see what happens, and then we can conclude a couple things. Let's say it's the case where x and y are both 0, but z is not 0. Okay? If x and y are both 0, then these equations vanish because it's just 0 equals 0, 0 equals 0. And we're left with this equation. But if x and y are 0, these also vanish. And so we're just left with these two equations. And the third one just becomes z squared equals 1. And this will immediately tell us that if we square root both sides, z has to be plus or minus 1. And so that already gives us our coordinates that will satisfy these conditions here. Because notice all it would do here if I entered 1 for z is just telling me what lambda is. And that's fine, but I'm not really looking for lambda in this case. I'm looking for x, y, and z. And if we assume x and y are 0, this system becomes this system, which concludes that a possible point, one of the points that I want to consider is the point 0, 0, and either plus 1, 0, 0, minus 1. So I'm going to write it like this, 0, 0, plus or minus 1. Okay, this will be one of the points that I want to consider. What about if maybe x equals 0 and z equals 0? Well, if x equals 0 and z equals 0, these vanish. I'll be left with this equation, and then I'll be left with y squared equals 1. And so the same process will happen. I'll be able to conclude that y is plus or minus 1. And the same thing will happen if y and z are 0. I'll be able to conclude that x is plus or minus 1. So if two variables are 0, we get these points as possible critical points for our function here. Okay? Okay, so this is the case when two of the variables are 0. What if we have the case where only one of the variables is 0? And let's pick one and see what happens. So if x is 0 and y is not 0 and z is not 0, then if x is 0, this equation will vanish and the x will vanish. And then we'll end up with this equation, and then just y squared plus z squared equals 1, which is what I wrote right here. So now I have to solve this smaller system. Okay, but we assumed that only x was 0. And so y and z are not 0. And so therefore, now I can isolate lambda because I can divide by y and z since we know they're not equal to 0. And so by doing that, I isolate lambda. These two are both equal to lambda. So then they're equal to one another. I divide by 2. And I'm able to get that y squared must equal z squared. And so since I want to satisfy this third equation, I'm going to replace the z squared with a y squared. And so therefore we get 2y squared equals 1, which means y squared will equal 1/2. I square root both sides. That will give me plus or minus 1 over the square root of 2. But then if I use this equation and I substitute these values in, I'm going to get that 1/2 is equal to z squared. And so then this will conclude that z equals plus or minus 1 over root 2. And so therefore, we have a whole bunch of points. When x is 0, y can be either positive 1 over root 2 and z could be 1 positive 1 over root 2, or you can have a combination of them being plus or minus or plus or minus. And so we have these 4 points given by the way I wrote it here. Okay, when it's 0 plus plus, or 0 plus minus, 0 minus plus, or 0 minus minus for these guys. So that's when x was 0, we were able to conclude these points. Well, the same exact thing will happen if y is 0, except that now it'll be in terms of x's here, and the x squared will be here. And this process will be exactly the same. So if y is 0, I will be able to get these other points. And if z is 0, the exact same process happens again, and I can find these other points. So if one of the variables is 0, I'm then able to conclude these possible points as candidates of having my maximal area, or sorry, my maximal value for my function, or my minimal value. Okay, so that's a whole bunch of points we have so far. We have, if two variables are 0, we want to consider these points. If one variable is 0, we want to consider these points. So the third case is if none of the variables are 0, and so therefore neither x nor y nor z equals 0. And so if none of them equals 0, I can isolate lambda and divide each of these equations by x, y, and z. I divide this one by x, I get this one. I divide this one by y, I get this one, and so on. Since all three of these are equal to lambda, I can then conclude that all three of these are equal to one another. I divide by 2, and so I'm able to conclude that x squared is equal to y squared, which is equal to z squared. And so then the y squared can be replaced with the x squared, and the z squared can be replaced with the x squared as well. Or I could have chosen the y's or the z's, depending. And so therefore I get 3x squared is equal to 1. I divide by 3. I take the square root. So you get that x has to be plus or minus 1 over root 3. But then you plug this value into this, and then you'll get that 1/3 is equal to y squared, because you're going to have to square this, right? You square either plus or minus, you'll get 1 over 3. But then this will conclude that z equals 1 plus or minus 1 over root 3. And similarly, you'll also be able to conclude that 1/3 is equal to z squared. And so z will be equal to plus or minus 1 over root 3. And so then you'll be able to get all these possible points as critical points in any type of combination of plus or minus, plus or minus. So this is another set of points that we need to consider when you're going to evaluate your function to find absolute max or absolute min. So see, it's a very dense algebraic problem, and there's a lot of kind of organization you need to do, okay? So to finish it off, let's evaluate the function at all those points. Notice that because the function itself, let me go back up to the function, is x to the fourth, y to the fourth, and z to the fourth, it doesn't matter if you plug in a plus or minus value for x or for y or for z, because they're going to be raised to the fourth power anyway, so they'll become positive regardless. So if I plug in the first set of points that we found, where 2 of the variables are 0, and I plug them into my function, I'm going to get 0 to the fourth plus 0 to the fourth plus this to the fourth is just 1. So for all these, you're just going to get 0 plus 1, or depending on which one you're letting equal 1. Regardless, the output value will all be 1 for these points. If you plug in the points you found where you let one of the variables equal 0, only one of them, that was this set of points. If you plug them in, for example, this one, you're going to get 0 to the fourth power plus or minus 1 over root 2 to the fourth power. That'll be 1/2 squared, right? Because if you square this, it'll be 1/2. But then you square it again, it'll be 1 to the fourth. Yeah, that's where I got that. Okay. Plus or minus 1 over root 2 to the fourth is again just 1/4. You add those up, you'll get 1/2, and that will be true for all the other ones as well. So you get 1/2, 1/2, 1/2. Okay, now when you plug in these points that you found, you're going to be raising plus or minus 1 over root 3 to the 4th power, which means if you square it, you get 1/3, but then you got to square it again, which will be 1/9. Yeah, okay. So then you're going to add 1/9 plus 1/9 plus 1/9. And so then you get 3/9, which is 1/3. And so when you look at all this here, you then conclude, hey, you know what? We found this is maximal right at these points. So it's at these points where you get an absolute max of 1, and at these points you have an absolute min of 1/3. Okay? And so that's how you would have to attack these problems for functions of 3 variables. They're a little bit more algebraically dense and a little bit more conceptually abstract. So you want to organize your work. All right, guys. And so we'll do some of this in class, and then we'll do some kind of summary of chapter 14, since this is the last section of this chapter. All right, bye.